So let us now come back to the third phase, the 1840s to 1880s, the period of the large manufacturing shops, especially railroads. So what took place during this period, and take a look at what took place during this period. It's important to recognize that, that the American style of manufacturing is experienced in the lives and work of mechanical engineers. Now, this is in sharp contrast with the French. If you look at mechanical engineering textbooks today, the theory that's presented is drawn from researchers, theoreticians who are almost entirely French. During the 19th century, the French developed theory in statics, in mechanics, in elasticity, strength of materials, hydrodynamics, thermodynamics, theories of machines, friction, structures, vibrations. And if at some point you have the opportunity to go to Paris and visit the École Polytechnique, as I did recently, you'll see statues of basically all these theorists because the vast majority of them were there. In contrast, historians haven't identified a single American as contributed to the fundamental mathematical foundations of mechanical engineering in the 19th century. In the American case, the American approach, in the American example, concepts derived from experience. There was something of a grassroots approach to knowledge and science. And so, for example, Calvert writes about the mechanical engineer Coleman Sellers. When he spoke of fundamental principles that underlie the theory of construction of machine tools, he did not mean mathematical theories. But what he meant were rather general concepts arising from this experience of using and designing machine tools, advanced rules of thumb in a way, or handbook theories. A lot of these fundamental principles were were put into to handbooks for American engineers. And so to Americans, formal theories, what were thought to be foundational, underlying fundamental theories, were basically condensations of experience, in sharp contrast with the French, who always would start with first mathematical principles and then derive their insights mathematically. Much of the history of engineering in the United States is basically is a story about progressive inroads of theory into engineering with periodic pendulum swings back into practical knowledge. Remember that our main historical ancestry here is through the British, whose interest is primarily in practical knowledge, with interesting links to the French and to some extent to the Germans. And not until after Sputnik in the late 20th century do we get that high commitment to mathematics that one sees in engineering in the United States today. So the link with the French is rather recent. Now, as I pointed out, the mechanical engineers, the role, the occupational category, emerges from the label superintendent, who grew up inside of the manufacturing shops apart from the master mechanic, on the other side of the growing boundary between management and labor. As Calvert writes, quote, "The term superintendent or motive power of engines and machinery referred to a salaried position, namely on the management side, approximately $1,000 to $2,000 per year in 1860, and a management position with technical prerequisites. It became one of the major fields for the development of the professional mechanical engineer. Despite his contact with management, this mechanical engineer at the same time always had one foot firmly in the shop." So the dual image of the superintendent as both technically competent engineer and manager is established inside of the manufacturing shops during the mid-19th century. Given that these people worked in shops, they had a deep commitment to the American style of manufacturing, the commitment to low-cost mass use very much characterized the engineers. As Chronakis puts it, quote, "The principal concern of American engineers, mechanical engineers, was to achieve material success, that is, to create successful artifacts, and to achieve commercial success in the marketplace. Theoretical knowledge, in contrast with the French, was considered important only insofar as it was essential to achieve these practical aims." commercial success. Note then the deep connection in mechanical engineering with business, the strong entrepreneurial spirit, as it were, in mechanical engineering. Now, you should also know that mechanical engineers also emerged to some extent and in a somewhat parallel way from the military, the Navy. With the growing use of steam engines to power warships, the Navy needed to make the job of running steam warships something more than that was appropriate for mechanics, something for officers, something for gentlemen. And so we find in the Navy the label assistant engineers appearing as early as the 1830s, with again by the 1850s many engineering slots being defined and as appropriate. As Calvert puts it, these engineers were trained in a more with greater scientific emphasis, but still nothing like the French. Calvert writes, quote, "Applicants for the engineer slots in the 1850s were given stiff examinations in steam engineering and in general mechanical engineering, covering such scientific subjects as mechanical powers, expansion of steam, strength of materials, resistance of solids through fluids, and geometrical figures." The major educational source of these mechanical engineers was the new Naval Academy, Annapolis. The Naval Academy trained the mechanical engineers around the machinery of steam power, just as West Point was training civil engineers. Note that in a way these engineers were managers of a sort inside the Navy, and when they left the service, they tended to become managers in the commercial world. And it's in that sense that the supply is a parallel one. Now, it's important to know exactly who did not serve as supply for mechanical engineers. The mechanics didn't basically not work themselves up to become mechanical engineers. Mechanics got located below the line separating labor and management as labor, judged to be lower class, with jobs that involved getting dirty, and a rather lower brow lifestyle, let's say. The engineers are trying to pull themselves up in contrast. Millwrights also never professionalized, locating themselves as skilled labor. Finally, the civil engineers. The civil engineers did not provide a supply source for mechanical engineers, in principle, and primarily because of the absence of an entrepreneurial spirit. Civil engineers were professionals working for the benefit of the whole, not for a particular company. As Calvert puts it, quote, "Civil engineering, defined in this country as the science of constructing canals, bridges, railroad beds, and aqueducts, might appear to have been a logical source for future mechanical engineers. Called into being as a profession by the canal and railroad building activities after 1815, civil engineers faced mechanical engineering problems in the building and maintaining of canals and railroads. They were called upon to do many types of theoretical and practical work which later were done by mechanical engineers. Civil engineers, however, were constrained by a considerable attachment to the idea that theirs was a gentleman's profession, and that mental and manual labor did not mix. In addition, those who were more professionally oriented had a distinctly anti-entrepreneurial bias. Civil engineers wished to be regarded as consultants, artisans, architects, but certainly not as businessmen. You see, the mechanical engineers, often trained as apprentices, were working alongside mechanics, but there was the social class differences that was that tracked the engineers into the higher positions and held back the mechanics. The civil engineers, in fact, actively resisted development of mechanical engineering as a distinct profession. Again, Calvert, quote, "The educational institutions and professional associations of civil engineers developed a disdain for mechanical engineers and other groups which formed professional engineering associations in the late 19th century, maintaining that the bulk of the membership in these newer occupations were not gentlemen in their sense of the word." So can you see how the civil engineers had worked so hard to develop a high status for themselves as gentlemen? They didn't want other groups breaking away and somehow competing with them. The leadership in mechanical engineering then basically became the shop-trained industry workers who had risen to the top of their organizations. And they established in the 1880s the American Society for Mechanical Engineers to compete with what had been around for a couple of decades, the American Society of Civil Engineers, with the goal of seeking professional status and autonomy for themselves. They were engineering businessmen, asserting their status as gentlemen alongside the traditional gentleman civil engineer. As David Noble writes, quote, "From the day of its founding, the ASME was little more than a social club run by and for the self-perpetuating oligarchy of a shop culture elite who had become leaders of industry." So think leaders of industry asserting their status. Now, the shop culture production of mechanical engineers over time is replaced by another whole source of engineers, but it takes a couple of decades for this to happen. The key stimulus for the development of school-trained mechanical engineers was passage of the Morrill Land Grant Act, which was the first foray of the federal government into state-level education, which funded what has become nearly all the big state universities in this country. For a detailed look at the Act, its implications, and a case study of one university, take a look at the day that's focused on that topic. As Calvert put it, quote, "Colleges and universities were quick to realize the possibilities of curriculum specialization and to develop a method of educating mechanical engineers when mechanical engineering emerged as an occupational specialty in the railroad, machine tool, and steam engine industries of the 1850s. So again, the schools are trying to move in to this territory. There was some push inside of the new schools to be somewhat like the French, to develop a more theoretically based orientation. And this was especially true at the Land Grant Institution of New York State, namely Cornell University. The engineering leader there, Robert Thurston, developed a theory that engineering education should be, in a way, a blend of French and German ideas. In his position, from France came an emphasis upon math and science and the concept of the high-level professional school with a hierarchical structure of schools. And drawing from Germany, looking to Germany, he drew the practice of setting up schools to train technical personnel at all levels, with the research institution at the top, namely the one that he was developing. Most other land-grant institutions developed an approach to engineering education that was much more practical, at least for the first few decades. But for our purposes now, the key is that the new school-trained engineering system provided a labor supply of mechanical engineers trained in schools for serving the rapidly expanding American industry in the late 19th century. Now, early on, initially, there was a great tension with the engineers trained in the shops. The shop people took the position, because of the emphasis on practical knowledge, that there's no way you can teach this knowledge in schools, in classes. How could a school pretend to be able to teach engineering? Meanwhile, the schools latched onto science as their vehicle for prestige and influence. And hence the students' experiences in shops was eventually replaced by student experiences in labs. Mechanical engineering and sometimes was renamed dynamical engineering to call attention to the theory of dynamics underlying it. So what we end up then in engineering in mechanical engineering in the late 19th century is what we end up with is a combination of shop-trained engineers and school-trained engineers competing with one another. As Noble puts it, quote, "The mechanical engineering profession was thus never a homogeneous body of professionals, but rather a loosely defined assemblage of primarily shop-trained industrialists, corporation executives, and shop managers on the one hand, and school-trained corporate employees on the other. Note that the students who came up through the school training tended to make their way into institutions on the inside, not becoming industry leaders and maybe not even aspiring for industry leadership, but rather working white-collar jobs as employees of the developing corporations. Over time, the school-trained engineers went out through the sheer force of numbers. By 1885, there are 85 schools. By World War I, there are more than 125 schools, and the number of graduates in engineering rapidly expands from 100 per year in 1870 to over 4,000 in World War I. Also, as Calvert puts it, quote, as calculus and other areas of higher mathematics became increasingly indispensable to the practice of mechanical engineering, the educational complex gained in prestige.